Okay, so now that we have our cool volume source here, which I think is going to make a really cool simulation once we get to it, let's make our collisions, or let's set them up. Now, Pyro is interesting because there's a bunch of different ways you can do it. I mean, ultimately, whether you're using rigid bodies in your smoke simulation, or you're using Houdini's fluid source that we've been using to generate collision volumes. The rigids would get converted into volumes anyway. Or the VDB method I'm about to show you, they all get turned into a collision field at the end of the day. I mean, hands down, don't ever do the rigid body way if you don't have to. Meaning, sure, if you have rigids and a liquid in the same simulation and you have to do it, then so be it. But as long as your rigid simulation is independent, or your animation in general is independent of there it is, of your smoke sim, which it usually is, then do it this way, which is make your collision volumes ahead of time and cache them like any other volume, just the way you would cache velocity or smoke or any or density. We can actually generate collision volumes. And the main difference between collision volumes and other kinds of volumes is these are signed distance fields. And if you remember, we're not going to use this node, but just to show you, we've been dealing with this kind of volume a lot, where it's just it's a fog in a sense. It's just these are just voxels that are storing how much density from 0 to 1 or beyond really is in there. But there's also this SDF volume, and SDF volumes are volumes that are representing solid geometry, which is why it kind of looks like this. These signed distance fields, signed meaning plus or minus, distance meaning every single voxel is storing the closest distance to the surface at that point. Meaning, where you see this geometry, really it's a bunch of squares, splats people call them sometimes, the distance to the surface is 0, because it's literally the surface. And that's what gets represented like this. Whereas the farther away you go, the more positive those distances become. You can't see it in here, but that's what's being stored. And then once you get inside, those numbers are becoming more and more negative, where the most negative voxel in the entire grid here is the point on the inside of the mesh furthest from the surface. These are used often to do quick collision lookups because they're literally storing whether you're inside or outside of the object, and also how far you are. So they're often used for collisions in all kinds of applications. And in any case, we're going to do that again here. Now, you could use the fluid source, our good old friend that we've been using to make density stuff. If you go over to container settings, you can change this to collision. And you'll see, oh look, there's that look again. It made an SDF for us, and it's calling it collision. And it's also making, it's recording the velocity. Pyro uses both the knowledge of whether a given voxel is inside or outside of a collision, and also the velocity to do its collisions. Meaning, so if objects are moving through space, such as these, it needs to push things out of the way, and that's what the velocities are for. But things can also be getting pushed at your object. Imagine a wind being blown at it. In that case, it needs to know whether it's going inside of the thing or not. And pressure calculations will divert it and change the velocity. So those two things combined, the velocity of it moving into smoke, and then the other way, where smoke is moving into it, is how collisions are robustly handled. Like in all of these cases, the higher the resolution that you make this, the more precise it will be. But the problem is, quickly, is that Houdini's native volumes, meaning not VDB, have a lot of problems. They can lead to, well, they're slow, at the very least, as you can see. This is very slow, and this isn't even really that high res yet. And then we also have some other weird problems going on. So this is actually the standard workflow, is using this. Fortunately, there's a better way, and that is to use what has superseded Houdini volumes in many respects, not entirely, but in many respects, are VDBs. VDBs are a fancier version of volumes. They're redundant with volumes in many ways, and in many more ways, they're superior. At the very least, they're basically always memory superior. In a nutshell, and we could certainly talk about this in depth later, or maybe in some sort of appendix. In a nutshell, what they do is they don't store values in a lot of places where they don't have to. So right off the bat, look at this crazy bounding box. It's not even trying to store volume data up here, over here, or in this big chunk. It's smarter than that. It knows that it can get away with a band. So here's the exterior band voxels and interior band voxels. What it's doing is, and you can use this VDB visualized tree, it's just being super smart about it, and it's breaking the space up into boxes. And these are the big boxes that really get smaller and smaller than this, until it only is ever storing the very small voxels worth of data right at the surface, and maybe a few bands out from that, meaning like rows of voxels. Whereas opposed to the regular voxelization from Houdini, it's storing everything everywhere. So what does that get you? Well, it means it can spend a lot less memory storing things. And if it can store a lot less memory, use a lot less memory, the effective size can be much better. So in fact, I'm just going to bring because ultimately that other guy, the fluid source, is using an ISO offset under the hood. So just as a quick comparison, if I go back to SDF here, so I'm going to say by size, so division size 0.1, and that's what this one is over here too. This is 0.1. So we can see this is 41 by 24 by 40, and this is pretty close to the same, 14,500 voxels. And this one is 39,000 voxels. So watch what happens though. So that was pretty fast. These conversions are pretty fast. But what happens if I go to 0.05? I had to think about that for a minute there. See? It's not too bad though. But watch when I go down to here. Now it's, because this is taking exponential